was described first by P.C. Mahalanobis in 1936. Very, very bright guy. And what it does is it is a scale invariant distance metric. And it also can handle things where, say, a training set is not spherically distributed around the mean. It does no good if your training set looks like this. You take the average Euclidean distance. This is still in the set, but it's way over here, and this one's way over here, and your point's over here. It doesn't work very well. The Mahalanobis distance, instead of testing the actual position, it tests the covariance, or how much the variables tend to change together. So, if we can. So, what you do is you build what is called a covariance matrix. The covariance matrix, and I'm going to get into covariance a bit more in the next slide. You take this covariance matrix and you use that as a weight for the average distance to all these other points. We still take, the distance to all these other points and we average them together, but we weight that average with this covariance matrix. And once again, we're not actually talking about a specific coordinate in this case. It's not in a geometric sense. It is actually in a covariance sense. And you can see all sorts of fun math there, and it's no fun for me to actually read it to you because that, you can read it yourself. But it's a really, really cool protocol, metric, and I really hope you guys look it up later. If that's the only thing you take away from this talk, that would be worthwhile. So if we can go one more. So covariance, that's the big deal for Mahalanobis distance. If you say something like, say you have the inner packet delay, and you have the packet size, and you note that as the packet size increases, the inner packet delay also increases, takes longer to send. And so what you have there is a positive covariance. And then say, for example, you have something where it starts to go down, and the other thing goes down as well. That's a negative covariance. And then say you have something, and this is the always fun one, where the two variables are completely independent. One goes up, one goes down. You have no covariance. It's a zero covariance. And so when you have this covariance matrix, and this covariance matrix is a matrix that maps every single coordinate to every other coordinate. So in this case, you're going to have 100 elements. You're going to have one for each coordinate and how it varies with every other coordinate. And then you take that covariance matrix, and then you take the all the points of all the training data as their covariance, and you measure them together, and then you take the distance there. And so now we have these two distance metrics, and that's really useful because we're not just relying on one distance metric. We're relying on two. One that handles non-spherical data sets, one that is very, very fast, one that is intuitively makes sense, and then one that handles things where variables are not necessarily independent. So we take these two distance metrics, and we take the two numbers for every protocol. So say we have in the training set 1,500 protocols. We do this calculation 1,500 times for that packet offset, and we get these two numbers. We have the Mahalanobis distance, and we have the Euclidean distance. And we say, if, for example, one protocol, say DNS, has the lowest distance in both metrics, we say that is we're pretty sure that that's DNS. We have, both metrics agreeing. Then what happens if you have, say, each metric identifies the lowest distance for two different protocols? Well, at that point, you have a bit of a conundrum. And we've left it sort of up to the network administrator there, whoever's using our software. He can say, we prefer to just pick the lowest distance. Whichever one gave the lowest distance, that's the one we want. Or you can say, we prefer to always choose the Mahalanobis distance if there's a disagreement. Or we can say, we always choose the Euclidean distance. And then finally, in the incredibly unlikely chance that both of those distances identify two different protocols and the distances are exactly the same, we just go ahead and flip a coin in favor of the Mahalanobis distance. But that way we have with these two metrics, it's great. It's just one more layer that we can make sure we're talking about one specific protocol. We look at all these different things. And can we go to the next slide? Okay. So that slide was, got a little ahead of myself there. But that's just talking about the Mahalanobis distance and how it can handle non-spherical data sets, things that are not distributed spherically around the mean. Okay, Rohit wanted to do this part. This was showing off the new 3D stuff that's all sorts of cool, so I'm going to hand it back to him.
Well, so since we have 10 dimensions, obviously you can't make a plot in 10 dimensions. What we chose to instead do to highlight how the data sets do lie fairly far apart visually is to choose 3 coordinates the entropy and the average packet sizes to both the client and server. And what I have here in the next plot, it's not a very pretty looking plot, but what you see is there is a cube for RTP and a cube for DNS, and in this slice of 3 dimensions, both these cubes lie quite far apart. And each point actually on that cube represents a packet trace we have for that particular traffic. So we have had hundreds of thousands of conversations which were recorded for RTP. So all of those points kind of clustered to form that cube there. And similarly, we had lots of DNS samples recorded, and all of the DNS samples lie a little different from there. So at any point of time now, if I want to, as he explained to you, the Euclidean and the other Mahalanobis distance, if I have another unknown trace which comes by, which I know is either RTP or DNS, and I plot it even in this particular 3-dimensional slice, and I find the distance for that trace from these two, I can figure out which cluster it would belong to and figure out which of the 2 protocols it is.
And so what we've got here is some actual results, which it's always scary to actually show your results. It's never fun, but this actually turned out really well. We were pleasantly surprised. So what we're looking at here is a NetBIOS packet capture, right? And we're looking at what its average Euclidean distance is from everything else. And so we fire this unknown NetBIOS PCAP. We're pretending we don't know what it is. We fire this NetBIOS PCAP through PISA, and it calculates all the distances for all these other protocols. And it says, well, the lowest distance, 676, is NetBIOS. And then you'll note that the next closest guess, which is NTP, was 1,100 units away in the scaled Euclidean. Very far away. So we're really sure that this is NetBIOS. And that was, when we saw that, this was actually one of the first experiments we ran, we were like, wow, that really works. Man, it's so nice to see an idea go from inception to completion. And that's what we saw when we did this. And can we go to the next slide? There we go. And so we've got Skype once again. And so we're running this unknown Skype PCAP. We're pretending like we don't know what it is. I think it was actually a conversation with Rohit's grandmother. But I didn't know. And we fired it through PISA. And PISA does all these tests and does all its magic and everything. And it comes up with these distance metrics again. And it says that its average Euclidean distance from the Skype cluster, 737. And its next best guess was 972 units away. So it's very sure that it is definitely Skype. It's not NetBIOS. And that's really good. And that was one of those things we wanted to make sure we tested with NetBIOS and Skype and all these other protocols, especially the ones that you never ever want to have misidentified. We really concentrated on DNS, on SMB, all that sort of thing, because we don't want you to have your network policy declare you can't use Skype and then suddenly nobody can connect to the file share. That would be bad. So, Ed, did you want to do the second one?
No, I can. You can.
All right. And so this one was also really cool. A coworker of ours does a lot of work with VoIP and steganography. And so we're looking at real-time protocol, right? Real-time transfer protocol. And what he was doing is he's running these experiments to put steganographic information and enclosing it in this RTP protocol and then sending off and hoping nobody notices. And steganography is the hiding of information in plain sight, like having a microdot or having every third word means something, things like that. But it's still, you have to look for it to know it's there. And that's what he's doing with RTPs. He's doing this steganographic insertion of data. And we wanted to see, wow, wouldn't it be cool if we could tell if he was doing this through statistical analysis? So not even just identifying the protocol, but identifying a protocol anomaly. So you can say, wait, this isn't really RTP. There's something fishy going on here. We should probably investigate this. And so that's what we did. We took, we had this huge training set of RTP and we fired it through. And then we fired through this RTP stream that had some steganographic information embedded. And what we found was that there was a 35% increase in the Shannon entropy. And that's because normally RTP is a very regular sort of thing. It doesn't have a lot of randomness. It's very normal. And all of a sudden, when you have all this other stuff that doesn't look like RTP, it suddenly increases the randomness quite a bit. It's not as regular as it once was. And so PISA was able to say, no, wait, this is an anomaly. There's a 35% difference along this axis for this protocol. You should probably look into this. And we were, of course, overjoyed that this worked, and my coworker was less than joyed that we caught him, but, what are you going to do? So he bought me a beer. That's, I guess, what you do. So can we go to the next slide? Oh, yeah, this is going to be Rohit. I'm going to let him finish up here.
So in conclusion, what you saw from various examples being presented for Skype as well as for the steganography is you can use this statistical framework to identify three things. You can identify the obfuscated and encrypted protocols. You can try to go and find anomalies happening over regular ports and regular protocols if somebody's trying to hide information or somebody's trying to do some covert channels. And we have a current version of the code which we will soon post to our dvlabs.tippingpoint.com website. What we would really want is if some of you would start using this particular script for the protocols in your network and also send us more training samples for different protocols, that would further enrich actually the signature set we are trying to build, a statistical signature set for various protocols which we are trying to build using this tool.
So that's a dictionary.
Yes, at the end of it, there will be a dictionary.
And any protocols that you send us, once they're run through here, they're completely anonymized. It's just statistical information. There's no data, left in there. We're not going to see what you were looking at or anything like that. We just see the statistics about the stream. So, and you could just say this was HTTP or this was whatever, and then we can say, oh, okay, great. There are the statistics for it. We don't actually know what you were doing. It's okay. We won't tell your boss. We won't tell your wife. It's all good.
So thanks.
And now, questions?
So you need to capture.
Yeah, well, okay. Yeah. Thank you. Woo!